Today we're happy to have Dranowski from the IAS, and she's going to be telling us about derived equivariant cohomology of the affine Grassmannian and Bezrukavnikov and Finkelberg's equivalences.
Okay, so thank you for the introduction, Mackie. And probably there'll be a lot of comments that the audience members might have throughout the talk. So maybe it's best if the little things that you spot as being incorrect or what not are saved for the break for discussion. Yeah, so this is the third in a series of a bunch of talks on this paper by Bezrukavnikov and Finkelberg, and it aims to try to summarize some of what they do. So the kind of philosophy of the paper that we've been able to extract on learning about it and working on it is that it's all about understanding some object by kind of enlarging it to more stuff, or deforming something that is very prevalent as a theme in algebraic geometry and elsewhere. So the goal of this talk is to try to make that precise, at least in one of the theorems that the paper establishes. Okay, so picking up from where Linyuan left off, let's see if my pencil works. Sorry. Okay, so last time, maybe I should highlight. Last time we were talking a lot about, not the best color, but anyway, last time we were talking about this column. So Linyuan told us sort of how we can go from using Ginzburg's picture from G check equivariant sheaves on the nilpotent cone to the derived category of geoconstructible sheaves on the affine Grassmannian via this constant restriction functor. So this co-G of a point has to do with the isomorphism of H Gur and the universal enveloping algebra of the centralizer in the Lie algebra of a principal nilpotent that Linyuan discussed.
But then not Koch G, but Koch for the centralizer.
Koch for the centralizer, yes.
The centralizer and also.
Yeah. It's not Koch G point.
Yeah.
It should be
well, centralizer semi-direct with the one-dimensional torus.
Yeah, so all okay, so this group here, sorry, so this should be a centralizer of this nilpotent. Yeah, something that I failed to correct in my slides. And yeah, there's a grading on modules over H Gur that we saw coming from this nilpotent that we can then turn on a G star action here on fibers. But I've kind of suppressed that from all of my sort of intermediate coherent or quasi-coherent categories in these pictures, because there's another C star action that I don't want to confuse that we're going to be interested in this talk. Okay, so just to recall, the notation D sub H here is bounded derived category of H equivariant sheaves, whereas in the bracket, like Linyuan was doing, I'll continue to do, this denotes derived on orbits constructible for this H action. Sorry, on H orbits. And so to go from this column that we learned about yesterday to the middle column, which we're ultimately kind of interested in. So this is what we.
By the way, so Tony asked a question. What does the dash arrow mean? So to So for the existence of these dashed arrows, you might need to add free or something.
Yeah.
Yes.
Yeah, so that's also true. These dashed arrows are kind of guaranteed by the gray arrows in all of these pictures, and they are equivalences on free stuff in our categories and our other categories. So there's some caveats, but anyways, they're arrows that are kind of obtained once the gray arrows are described, that are kind of guaranteed. So, okay, so today overall, we want this middle column, but it's kind of hard to go from the left to the right. So instead, we're going to enlarge the category that we're interested in to semi-direct GM equivariant sheaves. Thank you. And very easily kind of formally obtain that middle column by turning off that GM equivariance. So turn off where it stands for a loop rotation on the affine Grassmannian. So there are complementary objects in all of the columns to the things that we saw in Linyuan's talk. So here, so we want to describe this guy in terms of the Lie algebra of the Langlands dual of G. And we get this connection sorted by doing the same thing. We can relate HGO modules that again are graded, but I'm suppressing that, to coherent G-check equivariant sheaves on G-check. Also, there's a C-star action there. And in this bigger category, we can take before I outline that, we can again take GOGM equivariant cohomology and get sheaves on, so also we can get graded modules which we can view as sheaves on some space. And the spaces here are these spaces. And that is again related to coherent sheaves on G-check via some restriction. So these kappas stand for constant functors. Okay.
Why do we get quasi-coherent?
Let me not answer that question until the break. Let's discuss it.
Did you just say that the co in the middle means the co on the lowers the T check star over W?
Well, really total space of this guy, but yes, related to
the total space of the tangent bundle of that guy.
Yeah. Yeah, sorry, tangent bundle, not total space.
And the other one is actually the deformation to normal cone.
Yeah, so the stuff in the brackets is all related to these spaces, but what it is exactly we'll get to as we go. And why it's a Q here, okay, we can save that for discussion. Okay, so I'm sorry for this slide, but we're just going to read through it together and it'll be okay. So the goal, again, of derived Satake, so this is to quote Jordy in all of our meetings. So in the geometric Langlands program, one has triangulated categories. So these are derived, for example, this DGO GR. DG categories, so coherent sheaves on G-check, for example, and Hecke operators at a point, which are completely mysterious to me. But a fundamental question asked by Dranfeld is, what is the monoidal category of Hecke operators? And apparently this is the same as asking to describe this DGO GR G, and maybe in terms of the dual group. so from work of Ginsburg, BF deduced that this DGO G can be linked to conjugation equivariant coherent sheaves on the dual on the Langland's dual Lie algebra. But okay, unlike Ginsburg, as I tried to say in this picture from the previous slide, they rely on some deformation, or what they call asymptotics, coming from an added loop rotation action. And so this, I didn't say anything about this curly, this curly HC, but that category is is related to G-check equivariant sheaves on the Lie algebra of G-check, but it's some sort of deformation. Again, it's ad integrable G equivariant UG bimodules. Actually UG sub H bimodules. And yeah, in all of this, I may be missing checks, so it's an exercise to you guys to put them back where they should appear. Okay, and Bezrukavnikov and Finkelberg show that the full subcategory of semi-simple complexes in this enlarged category embeds into the category of certain coherent sheaves on, as Linyuan corrected, the deformation to the normal cone of T star mod W. And most of this talk will be, well, a good chunk of this talk will be on defining this deformation to the normal cone, because it is really key to their results. Okay, so, and finally, something that we won't get to, but that we'll hopefully get into next time, is that they managed to express equivariant cohomology of arbitrary, not necessarily semi-simple equivariant complexes in terms of Harish-Chandra bimodules, using the fact that there is an equivalence between this curly HC deformed version of co-G G equivariant sheaves on, this should be a G check, this should be a G check, but and semi-simple complexes in this enlarged derived category, generating it as a triangulated category. Okay, so onto our first formal definition here. So the Rees construction is what plays the role of deformation. So let me give a definition. Suppose that B is a Z-filtered ring. So we have an increasing filtration indexed by integers. And it's a separating filtration. So this just means that the intersection of all of those filtered pieces is 0. And the union of all of those pieces is B. And the unit is contained in the 0th graded piece. And if I take a guy in degree I and another in degree J and I multiply, then I land, well, in at most I plus J degree. Then the Rees ring I can associate to this such a ring. It's Rees ring defined by just as a set considering polynomials in an added formal H bar, such that the coefficient on H bar to the I is an element of the ith filtered piece. And this is called the Rees ring of B. And important properties of this construction is that H bar is central and not a 0 divisor, so it makes sense to localize. And when we do that, so we get B adjoin H bar inverse, so it's localizing at H bar. And we can also make sense of taking H bar to 0, that as the quotient of this Rees ring by H bar, the Rees ring of B. And what we get is exactly the associated graded ring of B. So important kind of notes about this construction that also go under the list of properties. There's no ring map from B to B hat. though there is one from the zeros filtered piece because it contains the identity and sort of goes into the zeros filtered piece of B hat. And there is a ring map from KH to B hat. Okay, so the geometric interpretation of this construction is the following. So suppose I have a subvariety Z that is the vanishing set of an ideal in some nice affine variety X. Then I can apply the construction to the coordinate ring of X by filtering it by the degree of vanishing along X, or sorry, Z. So this guy will be in degree -1, in degree -2, -3, 0, 1, and so on. And then what Bezrukavnikov and Finkelberg refer to as the deformation to the normal cone of Z in X is just a spec of this Rees ring of OX filtered with respect to the ideal of Z. So warning here, the reference that they give is to Fulton, but that reference describes a slightly different construction. Okay, so in particular, this deformation to the normal cone, because we have a map from KH to OX hat, is fibered over A1 with H bar equals 0 fiber equal to the what's called the normal cone, just the associated graded of, as we saw, of this OX. And in nice cases, so if Z is smooth, then this just recovers the tangent, the normal bundle to Z in X. But if it's not, then maybe you'll get something different. So here's an example of what you get if it isn't smooth, OX or OX hat. In the spec of GER, here it's fine, here it's OX. Sorry, just reading the questions in the chat. Okay, so, and if we look at any H bar not equal to 0, our fibers will look like copies of X. So maybe to add to this picture, more generally, we have our guy NXZ, this construction living over A1 and over A1 minus 0, we have X cross A1 minus 0. And over 0, we have the normal cone. Okay, so the situation that we'll be most interested in is that of the diagonal inside of X when X product, so say Y cross Y. So the ideal of the diagonal in a product is the kernel of the multiplication map. And in this case, we have the natural projections from Y cross Y to Y, which give us two maps from OY to OY tensor Y. But if we look at, if we take H equals to 0, so look at the associated graded with respect to filtration by this ideal, then the kernel is generated exactly by those elements where these two projection maps agree. So, and is a copy of OY here. Okay, so therefore we can say that there are two, well, sorry, let's ignore this part. Therefore we can say that this deformation, this Rees construction in this case is a ring that admits two actions of OY, which agree at H equals to 0. Okay. So the GeoGM equivariant cohomology of the affine Grassmannian can in fact be described in this way, and this is the first main result of the paper of Bezrukavnikov and Finkelberg. This is mysterious because it has to do with the fact that the two actions of geo-equivariant cohomology of a point on this ring agree when we forget this loop rotation. When we turn off loop rotation. And so this is a typo here. This should be homology, geo-equivariant homology. So one way to see this is to use the fact that this guy is commutative, but it's a fact that we just assume and that BF just assume. So, and this action comes from just this formal maps where I can consider the double coset space, which I'll be looking at if I'm taking geo-equivariant cohomology of the affine Grassmannian and its projection onto geomod a point in two different ways that gives me those actions. Okay, so, but having kind of recalled that fact, so theorem 1 of BF says that we have an isomorphism of the normal, of the deformation to the normal cone in T mod W cross T mod W to the diagonal. And with the two actions of HG of a point on the right-hand side corresponding to the two actions of OT mod W on the left-hand side that we saw in the special case of the geometric interpretation of the Rees construction when we're looking at the diagonal in Y cross Y. And correspondingly also the GM of a point action on the right-hand side corresponding to the formal K H bar action on this space. Okay, so in particular, setting H equals to 0 on both sides, we recover this fact kind of automatically, because in this case, the normal cone to delta in T star mod W, everything is smooth, is just the normal bundle. Okay, so I'm going to take a pause here. That's a lot to digest, and it's exactly halfway. That was not planned. Mackie, is it okay to take a break here, or is it too early?
No, this is good.
So Linyuan, your comment is that this should be.
You mean on this page?
Yeah.
So the purpose of this page is to prove that the two action of OY agrees on that OYO times, OY tensor OY hat agree, right? That's the purpose of this. The last sentence is the purpose of this.
Oh, shoot. I totally agree with you. Yeah. This does not make sense. It should be kernel. Yeah.
Yeah, but I mean that it's easy. It's so we don't that's delta star, but we actually I don't think we need that sentence. So my point is that so the geometric picture is so we can replace the y on the top left in the geometric picture with a normal cone of y inside y cross y as diagonal, and then we have these two projections, and the two composition from this normal cone to y are the same, and then we just so this is the geometric picture, which is very clear, and then we just make this geometric picture an algebraic one. So we get OY, then double arrow to OY cross OY all times OY to this deformation to normal cone, and then to the special fiber. And so this is also this algebraic picture corresponds exactly to the geometric picture, and so which means that the two composition on the algebra side also coincide with each other. And this
so I agree that this picture does not reflect the algebra maps on the right hand side, but it does imply what you are describing. Yes.
And then we can remove the second sentence. So the second sentence with kernel PR star, blah, blah, and then write directly the last sentence. So these two actions agree at h bar equals to 0.
Okay, I mean, I would just emphasize this. And I won't rewrite that now, but yes, you can do that as well. So this map, just like this guy has, of course, a copy of OY sitting here. So that's that map. And then the point is that when we take the associated graded, that first piece is again a copy of OY.
No, we don't need to take the first piece. So this girl OY OY tensor OY thing. So this is just the coordinate ring of the normal cone. And
yeah,
so,
I agree.
Yeah, so because what we want is two maps from OY to this zero fiber, which means girl OY OY tensor OY, such that these two so these two arrows gives two actions, and such that these two arrows agree.
So the composition is those two maps. I think we can leave it and maybe discuss.
Okay,
yeah.
Let's start back up.
Okay. Okay, so if there are no questions, so this again, so this is theorem 1, and it has to do with this Rees construction, and our first order of business for this part. For the second part of the talk is going to be to try to give a sketch of a proof of this theorem. So the preliminaries that we need is that we can, first of all, rewrite HGO GM of a point as HG of a point tensor with GM of a point, and roughly this is because GO is you write a plus. It looks like G plus some unipotent stuff, namely the kernel of the evaluation of that formal variable T at 0. And this unipotent stuff does not contribute to the equivariant cohomology because it is kind of its own, it admits an action of itself that is free, and it is simply connected. So EGO GM.
It is contractible more than simply connected.
Thank you. Yeah, it is contractible. Just by definition as the kernel of this evaluation. So under this C star action, but so this space is the same as E G cross GM. Okay, and then this factor is equal to HT of a point W invariance. And this is, again, very roughly because EG mod G is the acyclic quotient of, sorry. Of EG mod NGT, and this is a W cover, although personally I don't totally understand what the fibers of this map are, but from these observations we can get this relationship, and this is just and then finally, this affine Grassmannian is equivariantly formal. So in particular, GO, GM, equivariant cohomology is torsion-free, and we can essentially rewrite this as this space with an action of this this guy from upstairs. Okay, so with these facts in hand, we can prove this theorem. So HGOGM is now, we can view it as a module over HG cross D cross GM of a point. And we have this mysterious fact that when we set H bar equals to 0, well, first of all, we recover HGO of GER, but the two actions of HG of a point on HGO GER agree. Therefore, from the picture that we were just discussing, this this kind of well, this map of the three actions just taken together factors through. So there's a map to this Rees construction. Oops, sorry. And this guarantees a map from this coordinate ring of the normal, this deformation to the normal cone of the diagonal that we're going to call alpha as BF do. So yeah, these three actions factor through the Rees ring with respect to the filtration by, and again, this doesn't quite make sense and should be a delta star. But now that we have this map alpha, the rest of the proof is in showing that this is an isomorphism. And so the first step in that is to show that it is injective. So because GER is equivariantly formal, it suffices to prove this on localized cohomology on the right-hand side, which we kind of match on the left-hand side and define a localized version of this map alpha by doing that. But first, let's recall what is the localization of HGO-GM. Well, at T cross GM equivariant fixed points, which are exactly given by the weights of T, we get just a product of the fraction fields of those weights of T cross GM, which is Lie algebra of T cross A1. And then doing the same thing on the left, tensoring over with O T mod W times A1 with this fraction field, we have to see that we get something that we can kind of map into this space now injectively. So how to see that? Well, we first observed that if we have a function on T cross A1 or cross A1 minus 0, so over general points of this deformation construction, it's determined by its restriction on to infinitely many points, assuming infinitely many points of certain sets, assuming that the union of all of those sets is dense in this is Zariski dense in this space where we are interested in the values that our function is taking, which is true for this set. So we're going to consider this kind of contrived looking set that depends on the lambdas showing up on the right hand side. So taking x, y, and a such that x minus y is a times lambda. And then basically just restricting to W invariant functions on T cross T and passing that through this tensor product over here and sending its value into this product over here. Wouldn't it be enough just to prove that the hum is an isomorphism modulo H bar, thanks to the grading and the target being CH flat? I'm not sure. Okay, so Ivan poses a easier solution. So maybe there is an easier argument, but this is, I think, the argument that BF have in mind.
Can you say what does equivariantly formal mean and how are you using it? Why is it true and how are you using it?
What does equivariantly formal mean and how are we using it? So I think, like for us, it's the important thing is that this spectral sequence that you might use to compute equivariant cohomology degenerates on the E2 page. And well, that you can do equivariant localization. That's what it is needed for.
I assume it means the cohomology ring is formal. Is that? But is that right? And does it? And why is it true?
Why is it true?
It's just so equivariantly formal means it's a free module over the equivariant cohomology of a point. And as Anne says, that's the same thing as the spectral sequence degenerating. And it's true in this setting either for weight reasons or parity reasons. So you can imagine the E2 page of the spectral sequence has only entries where the sum of I plus j is even. And so the differential has to be 0 for silly reasons. But equivariant formality is a priori not linked to, like we say formality, but it doesn't mean the same thing as we normally mean under formality with like DG algebras, etc.
Oh, it doesn't mean the cohomology ring. Like, okay, it's formal.
Yeah.
Okay. Thank you. Okay, so moving on, the last step would be to show that this alpha log is surjective, and I will not go through the argument for that, but the method of, or how BF argue this is they compare sort of h-graded dimensions of either side, where this is in quotation marks because maybe really we want the weight of h bar in this ring over which our cohomology is a free module. So we'll find that they are equal and or maybe up to some shifts, and that gives us the isomorphism. Okay. So for the rest of the talk, so what we've just done so far is describe this GeoGM in such a way that we can imagine that the left-hand side of this triangle, so this category, has nice properties, and in fact it does. It's a full embedding on the full subcategory of semi-simple complexes into what was on the first slide, which would really have been this guy. Kind of, again, that GM is not to be confused with that GM. But while what we really want is this horizontal arrow relating it to this additive category, for the rest of the talk, we'll instead give some idea of this arrow into this additive category, and kind of piecing together these two, the dotted equivalence will be guaranteed, but maybe that can be discussed by Jitsu next time. Okay, so the first thing is to kind of define what is this curly HC on the right side of the triangle. So what is this HC H bar? And it's defined in terms of the, well, as we said, this is sort of like a deformed version of Harishchandra by modules. And it comes from, first of all, deforming the universal enveloping algebra of our group, using again a Rees construction, but this time with respect to a degree filtration. So if you're careful, you'll notice that kind of the grading is going in the other direction. And considering G-check modules over this tensor product now, such that the actions, so the actions are compatible. Oh, sorry, before we go on. So this is basically the definition of this curly H CH bar. And it's a category and it contains ordinary UG bimodules. For general values of H bar. And then, yep.
Well, may I ask a couple of questions?
Sure, or make corrections.
Do we assume that these bimodules are finitely generated? Well, as bimodules.
I think so.
And then the category of usual bimodules, it doesn't sit inside of this homogenized category. It's rather a quotient.
Yeah. Sorry. Okay. I won't write that, but yes. Okay, so if there are no more questions, so again, we had this triangle on the previous slide, and Bezrukavnikov and Finkelberg defined a map kappa H bar from this category of bimodules to quasi-coherent sheaves on T mod W cross T mod W cross A1 by what they call the constant functor kappa H, but is maybe should be called the Kosten-Zergel function functor according to Ivan. So the definition is that we take a module for UH tensor UH and then we tensor it over UN minus with a character psi of UHN that sends sort of all of our root vectors generating the unipotent subalgebra to 1. And then we take n invariants. And what Bezrukavnikov and Finkelberg show is that kappa H is a fully faithful embedding on freely generated Harishchandra, or what they call asymptotic Harishchandra bimodules, so UH. UH bimodules. And this is proved using transversality of the Kosten slice, which Linyuan kind of told us about last time. So we have this slice. I'm not sure what the notation we used anymore is, but I'll use sigma inside T, which is a section of T mod W, and it's defined as E plus add f. And it's maybe a little bit opaque to see how this falls out of this definition, but or how fully faithfulness rather can be proved using the constant slice. So I'll just finish by sharing another definition of this functor. So one can equally define kappa h by a quotient, and correct me even if I'm wrong in anything I wrote, but we can look at a reduction. So where we fix our character as before, and we take m quotient n minus psi n, and then take n invariants. And for example, if our module is just UH itself, then we should recover the center of UH. Okay, so I think that I'll actually stop here and we can discuss maybe further these definitions and the ideas behind the fully faithfulness, but or the equivariant cohomology that people in the chat are still on about. So thank you, Meki. I think I'll stop.